All right. So moving forward, we are talking about probability today. Okay. You guys are going to be able to find the probability of any two or more events. This is the stuff that we talked about last year. For those who weren't in class last year, but it's pretty much your basic probability knowledge. Okay. And then involving Venn diagrams, sample spaces, tree diagrams, and then after we get through that, then we'll go into the stuff that we haven't learned yet. So we are finally on the last bit of stuff from last year. Okay, then we'll go into stuff that no one has ever learned. Okay?
Unless you took AP.
No, not even took AP.
Maybe you took IB.
Or AP statistics. That's the only time you actually see this.
I wanted to take
Right.
it.
So
Nice try.
probability. You guys are gonna be able to again find the probability of any two or more events. So let's start out. Do I expect you to write down everything? No, but if there's something that you didn't know the definition of, hey, why not write it down? Okay? But an event is an outcome from an experiment, okay? So if you flip a coin landing on a head or landing on the tail, that is an event, okay? That is to be the outcome of the process of flipping a coin, okay? That's what an experiment is. It's a process in which you get an outcome. So the experiment, flipping a coin, the event, getting heads or tails, okay? And basic probability is n of A over n of U. N representing the number of ways of an A can occur, that's your numerator, and the denominator is the total number of possible outcomes. That is what basic probability is. If you flip a coin, what's the probability of getting a head?
50%.
50%, or as a fraction?
1/2.
1/2. Okay? So we guys already know this. If probability of an event is P, and in trials, you would expect the event to occur N times P times. Alright? So, if it asks you to figure out, okay, what's the probability of getting a tails? 50%. So if you flip a coin 50 times, what would you expect to get? How many tails?
50 or 45.
25 times. You should expect to get it 25 times out of the 50. That is what expectation, the most basic description of expectation. The last little bit, A prime that stands for complement is the complement of A. The probability of a complement is 1 minus the probability of the event actually happening. So that means the probability of an event happening plus the probability of its complement should equal 1. Okay? Prime example of that is if you have the probability, if A is the event of
How can A be the event?
rolling a die and getting so say your experiment is rolling a die and your event is getting a 1. What's the probability of getting a 1? 1 out of 6. So then its complement would be everything rolling the die and getting everything but 1, which would be 5. And if you notice, 1 out of 6 divided by 5 or 6 does add up to equal 1. And of course 1 minus, did I say it wrong?
You said divide.
If 1 over 6 is divided by 5 over 6.
If 1 over 6 is added to 1 over 5, it equals 1. And then of course if you did 1 minus 1 over 6, you would get 5 over 6. So that's the whole idea behind complement. Again, any questions? Alright, I'm going to do a little bit of whiteboard practice. Not going to corporate this, it's just to go over the idea of getting basic probability. Alright, so getting back into the notes, addition rule is one of the things that you can use when you are dealing with probability. It also kind of plays into the whole Venn diagram situation where you have your universal set, hence the U. You have two different things happening. This right here means what? Union. That means everything included in A and B. So the union of A and B would technically be what's shaded in yellow. Okay, that's what's shaded in yellow, the union of B. And the formula says that you can figure out all the things that are in A and B by doing the probability of A, just A, plus the probability of B, minus the probability of A in B. What does that in mean? What's that symbol mean? Both. Also known as, starts with I. These two circles are intersecting. So this is called an intersection. So the intersection of the two. Because basically when you do the probability of A plus the probability of B, you're basically counting twice with the two having common. So you want to make sure that you subtract their intersection, which is the part that you see here. Okay? Questions on that? We're going to look at an example. If you want, you can add this example into your notes. If you want to do it on your whiteboard, it's fine. Pretty much all the examples that are going to come from here on out, you can add them into your notes if you like. There are some longer ones, so I would suggest that you watch some video if you want to get those down and just get to work. But we have events A and B are given such that the probability of A is 3/4, probability of A union B is 5/4, and the probability of A intersection B is 3/10. It says find the probability of B. Now granted, you have all the pieces that go along with your addition rule, which is what I'm writing here. So pretty much it's just a matter of plugging in to find the probability of B. So that's what I want you guys to do. Find the probability of B. Plug in what you already have and solve for the probability of B. Sorry, messed up on the formula. It should be intersection here. I think I said it, but
Hey, I gotta redo my problem now.
well, you should have been able to get the thing. Okay. You get everything to one side. Your common denominator is going to be 20, so that's 16 minus 15 plus 6 equals the probability of B. And so then 4, 6, 5, 15.
Yeah, that's right. Because you have 1 for 6.
Yep. So
And I didn't realize that was 1 for 20. I went to 40.
It's not that
All right.
much better.
mutually exclusive events. Okay? Mutually exclusive events means that you have two events that have nothing to do with each other. Prime example, doing the card thing. Aces, probability of getting an ace and the probability of getting a king. There's no such thing as an ace-king card in a deck of cards. So these are examples of mutually exclusive events. Basically, the probability of their intersection is equal to 0, meaning that they have nothing in common, which they don't clearly. You can see the representation of the cards in there. And then, of course, the union of the two events would be the probability of A plus the probability of B happening. So yes, aces and kings, those are an example of mutually exclusive events. And that is how you would determine if something is mutually exclusive or not. Look at an example. Two events, N and M, are such that the probability of N is 1/5, the probability of M is 1/10, and the probability of N union M is 3/10. Are N and M mutually exclusive events? Okay? Remember, to be mutually exclusive, that means that their intersection, sorry, let me use N and M, has to equal what? 0. And then their union, them added together, exactly. So let's double check these, okay? Let's start with this one because we already have all the information. The probability of their union is 3/10. Probability of N is 1/5, and the probability of N is 1/10. So we basically are showing whether or not these are mutually exclusive events. When I add 5, 1/5, and 1/10 together, is that 3/10?
Yeah.
Yes, it is. This will be 2 plus 1/10, which is indeed 3/10. So that part does check out to verify that they are mutually exclusive events. Now we just have to show and prove that the probability of their intersection does indeed equal 0. What would I use to actually do that? What could I use to show that the intersection? Huh? The addition rule, which says the probability of their union is equal to the probability of each one added together minus the intersection. Well, considering that we already just added that these and found out this was 3/10, when I solve for the probability of their, I keep doing this, why don't I keep doing this? Intersection. When I subtract this over, this does indeed equal 0. So yes, these are mutually exclusive events. That's how you show it algebraically. Those are intersections in the purple. Questions? All right. Product rule, aka if events are independent, their intersection is equal to the product of the two together. Okay, that's how you determine the two events are independent of each other. What does it mean to be an independent event? Say again? They have no effect on each other. So one thing happening has no effect on the other, such as flipping a coin and rolling a die have no effect on the outcome of what's going to happen. Okay? However, if I have a bag of balls, different colors, and I pick a ball out and I don't replace it, well then the probability of getting the next ball is affected by that. So that would be an example of independent events versus non-independent events. Make sense? Okay. So we're going to look at an example. Okay, I want you guys to do this one on your whiteboards. These are independent events. So to figure out the probability, you do multiply them. As 1 has to get ahead, and 5 6 that you do not get a 6, so that is 5 over 12. Questions on independent events before we move on to conditional probability? Conditional probability is when one event is dependent on the other. And that is the formula for conditional probability. Anytime you see this vertical bar, that is indication that you are dealing with conditional probability. And the formula is the probability of the intersection of the two events happening divided by the probability of the given condition, which is always the part that follows the bar. And so the wording that could be in the problem is given such that all those things indicate conditional probability if the notation is not already given for you. All right, here's an example. It's your choice if you want to write it down in your notes, but like I said again, I will post the video so you can
That must be the junior class.
have it there.
That must be the junior class.
No, they have like a whole thing. This is like you see is note example, note example, note example. You've already been through this.
Talking about 100 students in the IB examination.
We'll see. We'll see condition. But in a large graduating class, there are 100 students taking the IB examination. 40 students are doing Math SL, 30 students are doing Physics XL, and 12 are doing both. A student is chosen at random. Find the probability that the student is doing physics, given that he or she is doing mathematics. That right there, there's that notation. Given that, this signifies conditional probability. All right? Now, the only thing is with conditional probability, let's set this up. Okay?
Which one would be A?
Which one? I was about to ask that question. What is the condition? Doing math. So math is the part that follows. Math is the B in the formula. And then taking physics. All right? So in our formula, we're going to need the intersection that a student takes physics and math and divided by the probability that the student takes math. Okay? So how do we figure out this probability? What do you think?
I made a Venn diagram.
Venn diagram would definitely be a good thing. Especially because all we have are numbers here. We really don't have probabilities. We know there's 100 students taking the IB exam. 40 students are doing math. 30 are doing physics, 12 are doing both. So you already know that 12 should be where?
In the middle.
In the middle, because they're both doing it. Now, the 40 students who are doing math, that also includes the ones that are doing both. So how many just do math? 28. So this part right here is only for those who are doing just math. How many are doing just physics? How many?
18.
18. You subtract 30 from 12. Now, does that add up to be 100?
No, that's not. That means there's some outside.
There are some outside. Now, I know we really don't need to be concerned with the number on the outside, but, this is just part A and B of probably what could be an A through F problem. So, how do I figure out how many take neither physics or math?
Add those together, subtract it from 100.
Which is?
I think it's 42, right?
Is 42. Okay? So, a student. Alright, so, what is the probability of the intersection between physics and math?
12.
Out of 12 out of 100, so that's your numerator. Now you have to divide it by the probability that a student takes math. How many math students are there?
40.
It is 40, not 28, because it's technically all the math students. So it's 48 out of 100.
Whoa, 48, 40.
I'm sorry, 40. I saw the 8. My apologies. 40 out of 100. So when we divide, we get,
3 over 10.
and that came from what?
Well, I just put 12 over 40.
That works too.
Yeah, same answer.
That's what you'll get because they both have the same denominator, and both of them are divisible by 4. So that is your probability. Questions on that?
One question.
Yes.
How come we made that's so
Because that was the part that followed the given that. The indication that we're using conditional probability, that is the condition. It has to be a student who's taking math that takes physics. Now, are they independent of each other? I'm gonna let you guys do that one on your whiteboards, okay? We already talked about what makes something independent, so I want you guys to tell, basically do on your whiteboard whether or not they are independent of each other. Yes, they are independent of each other. Because remember, to be independent, that means that their intersection, so physics and math, has to equal the probability of their products, correct?
correct.
So we already know the intersection is 12 over 100, and then we're going to multiply the probability of P, which is 40 out of 100, and
30 out of 100, but they multiply them the same thing.
exactly, that's 1200 over 10,000.
Or you simplify the 10.
Questions? Not too bad, right? Okay. You don't have to write this down. These are just examples of a sample space and a tree diagram, okay? These are just different representations of data, okay? Because if you have 2 die and you roll them, they might ask you, to find like the sum, was probably the sum is bigger than 10 or something like that. A sample space is a good way to organize that data. Sometimes it's with the numbers, sometimes it could be represented like with dots. It's just a different way to represent a large set of information. Tree diagrams. These are always nice. Okay, say you have a group of people that you're trying to pick for a committee. You have boys and girls. You have probability that you pick a boy and a probability that you pick a girl. Once you pick them, you still have to pick, 3 more. So this is an example of picking 3 boys, 2 boys and a girl, a boy, a girl, then a boy, so on and so forth. These are your different outcomes. Again, tree diagrams is another way to represent a set of information.
I remember that problem from last year, the one with the ball, the red ball. And it had like 40 you could draw, and Manny found the quickest way to do it.
Because it was a compliment type thing.
Yeah, and
So you
everyone
couldn't
was
do
making the huge diagrams out, and then Manny found the simplest way to do it. It's just like you just followed one line.
Because we realized they were all the same.
Yeah, it was.
So we're going to look at an example of a tree diagram. We're going to look at an example of a tree diagram. It's going to be the last thing for today. Okay? The probability that Andrea passes her French exam is 4/5, and the probability that she passes her mathematics exam is 9/10. What's the probability that she passes both exams? Then we're going to copy and complete the tree diagram, show the probabilities on each branch, and then we're going to find the probability that she passes one exam but fails the other. What are you going to use to determine A? No. Yes, you can use B to help you determine A. Yes, you can. But what's another way you can determine A?
Just use the stuff in the
Mm-hmm.
question.
They're independent, so the intersect is sometimes each other.
Yes, they are independent of each other. So to find the probability that she passes both exams, you just multiply the two together, which is a total of
36 over 50, which is 18 over 25. You can't go, well, we can go 6 over 25 over 3, which is
Too much.
7.8.
too much.
No, 8.8.
Okay. One thing that you need to worry about when you're completing a tree diagram is that the branches have to what?
Add 1.
They have to add up to 1. So the fact that she passes French is 4 out of 5. She's gonna fail French
2 out of 5.
1 out of 5.
But that is, I know.
A mess. Okay. And then she passes math 9 out of 10. So that means she could fail math 1 out of 10. Now this one here, this one's blank. What needs to go here?
Pass, math, fail.
Passes math and then fails. And let me not even do this. I don't want you guys to do this. Please write it out. Don't try to abbreviate anything. If they write it out, you write it out the exact same way they wrote it.
I put PM, FM,
What are these branches?
9/10,
9/10 and
1/10.
1/10. So you have 4 different outcomes that could happen. You have 4 different ones. This girl, she could pass math and pass French. What's the probability that she passes both these subjects?
18 over 25.
It is 18 out of 25 because, well, besides that we did already over here, but you can just multiply along the branches. Anytime you're trying to figure out the total outcomes, just multiply along the branches. What about her passing French but failing math? 4 out of 50, so 2 out of 25. She could fail French but pass math, which is
9 out of 50.
9 out of 50.
3 out of.
Oh, that one doesn't reduce nicely? Okay, so I'm going to leave this then.
Yeah, that's why I left 4 out of 50.
So they all reduce nicely. My mistake. So this one is 36 out of 50, 4 out of 50. What's the probability that she fails both? 1 out of 50? That's actually not bad. 1 out of 50 shot. Chance that you might fail both of your exams?
I like this.
Now I was asking you, what's the probability that she passes one but fails the other? 13 out of 50 because she could pass French but fail math and then fail French but pass math. So you gotta look at both of those probabilities together and add them. So yes, 13 out of 50. That she will pass one but fail the other. Alright? Clear your whiteboard. I'm gonna give you a few more based off of this one situation.